let S be a subset of Rn. If S is compact, so also is the convex hull of S. Now here, this will have a short proof, but will utilize several theorems. Now let us first define this as the set of all lambda in Rn plus. Now this was the set of all n vectors that are non-negative, that is, each component is larger than or equal to 0, such that lambda I from 1 to n is equal to 1. Well, this will clearly be bounded, and it's easy to show that it's closed as well. So check that. Now let me leave this out. Let me introduce this later. Let this be just delta, but it depends upon n. And n is the dimension of this. Delta is closed and bounded. So delta is compact by Heine-Borel theorem. So this actually gives us let me take this in Rn plus 1. Now this will give us the set of all the components of any lambda in delta. That will give us a set of coefficients that we can use in forming the convex combination of n plus 1 members taken from cap S. Why n plus 1 members? Well, by Kara-Toyotori's theorem, we have seen, well, convex hull of S, that will be equal to the collection of all convex combinations of any n plus 1 members belonging to cap S. Now, delta is compact by this. Now, set S n plus 1 is the Cartesian product of S with itself n plus 1 times. Okay? Now, assume that S is compact. Now, this will be compact by Tikhonov. It's a product of compact sets, but if we take its product with delta as well, is compact with respect to the product topology of what? This is in n plus 1 in Rn, in R2n plus 2, but we know that the product topology there is just the usual topology on R2n plus 2. This is in Rn plus 1. Well, no, each of these is in Rn, so we'll have n times n plus 1 plus n plus 1. So that will be the dimension of this. By Tikhonov. Now define f on delta cross Sn plus 1 into Rn by, now we will take some lambda from here and n plus 1 vectors, each from S. So before defining that, let me write at each lambda in delta and y1 up to yn plus 1 in Sn plus 1. Well, we will now take the convex combination of these yi's, each y super I, that's an n vector itself. It comes from S is in Rn, I from 1 to n plus 1. What can we tell about the continuity of F? Well, in one of the exercises, in your exercise set, well, in Rn, scalar multiplication is continuous, vector addition is continuous, but this just consists of scalar multiplications plus adding such scalar products. But as that's in the exercise set, you may or may not have gone through that exercise. Check that F is continuous on its domain. But what happens to compact sets under continuous functions? Compactness is preserved. So f of delta Sn plus 1 is a compact subset of Rn. Okay, but we wanted to show that convex hull of S is compact. Is this somehow related with the convex hull of S, f of delta cross Sn plus 1? So it is the set of all such convex combinations when we each time take n plus 1 members from cap S, and well, these are just non-negative coefficients which all add up to 1. But what does that tell about the range of this f of delta? Well, this is just the convex hull of S by Koray-Theodoros theorem. So, convex hull of S is compact. Okay? So we have used here Heine-Borel theorem, Tychonov's theorem, Koray-Theodoros theorem, and preservation of compactness under continuous functions. So that powerful toolbox made the proof of this easy. Okay? Okay. Any questions about this? Now, let's get back to our problem of 3 points in the plane which are not collinear, that is, which do not lie on one and the same line. There is no such line. So these are non-collinear. But since the dimension of R2 as a real vector space is 2, well, any 3 vectors, any number of vectors, well, where the number is larger than the dimension, they will be linearly dependent. So these are linearly dependent, but not collinear. So the question now is, can we define collinearity or equivalently non-collinearity, and can we relate it to linear dependence or linear independence? Okay? Now here, if these were collinear, say if there existed some line such that these 3 points lie on the same line, then one way of relating this to linear dependence, independence, would be not just considering these 3 points themselves, but say take P1 minus P3, which will be this vector, and then P2 minus P3, which will be this vector. This is P1 minus P3. Now points and vectors are the same, so this is P2 minus P3. Well, we could have done this taking P1, for example, then P3 minus P1, P2 minus P1, but no matter which one of the 3 we take, and we subtract that from the remaining 2, the 2 vectors we obtain will be linearly dependent, because one will be a scalar multiple of the other. So, well, if this does not happen, that is, if I take P1, say, P3 minus P1 and P2 minus P1, if they turn out to be linearly independent rather than linearly dependent, and as in here, well, that will be the case here. P2 minus P1 and P3 minus P2. Pictorially, these will be linearly independent, these 2 vectors. So we will refer to that as the original collection, P1, P2, P3, being affinely independent. So we'll introduce the notions of affine independence and affine dependence. Now, although this is, well, we could have taken what we have observed in here as the definition of affine independence, but we will take another definition, but then it will turn out that the rule, the condition that we discovered here, that's equivalent to the definition of affine independence, I will give. Now let x1, xl be in Rn. What's the definition, the analytical definition of these to be linearly independent? Well, from linear algebra, if I take any L real numbers, C1 up to Cl, and form C1x1 plus C2x2 plus CLXL, if I set that equal to the zero vector, that equality should imply that all the coefficients, C1, C2 up to Cn, they all must be equal to zero. Now, the definition we will adopt here for affine independence will be similar to that, but we will put one further condition that the coefficients we use will have to satisfy. But let me first write that. We say that x1, xl are affinely independent if now I will write the condition. For all I in 1 to L, Ri is a real number. Rixi, I from 1 to L is equal to 0. Now, if this implies that all Ri's are equal to 0, then that means x1 up to xl, they're linearly independent. But we make this stronger by assuming that the coefficients we take here, they all add up to 0. Now, this should imply that for all I from 1 to L, Ri equal to 0. Here we have a stronger condition, which implies the zeroness of all coefficients, a stronger condition than in the definition of linear independence. Thus, linear independence applies affine independence, but you can easily see, as in here, well, these will be 3 points in R2, which are not called linear, can easily be checked to be affinely independent, but they will be linearly dependent. Okay? Now, linear independence that will imply affine independence. Here, P implies Q. Q is the same in both cases, but P is stronger in the affine independence case, while the condition corresponding to that for linear independence, that weaker. So P prime being weaker than P, then P prime implies Q, that's stronger than P implies Q. That's just what that is. But now we can come back to this and obtain the description in here being equivalent to the definition in here as a proposition, as a result. Now let me give some symbol to this initial segment of natural numbers. Let L be a natural number, and with L larger than or equal to 2, set IL equal to this initial segment of natural numbers. For each I in IL, let xi be some n vector, some member of Rn. So we have here x1, x2 up to xl. Now, x1, xl are finally independent if and only if the condition here holds. Now, what was the condition here? For any k in IL, I subtract x sub k from all the x sub i's when I is different than k. xi minus xk such that I is in IL minus k is linearly independent. This is just writing what we have observed on the picture in a more general. There we had 3, R2, but this is Rn, and we have L vectors. But this should be larger than or equal to 2. Well, if it's 1, then this will be the empty set, because there will be no I different than 1, so there will be, so, okay. Now, proof. It has 2 directions, but both are similar to each other. Now, let's assume that x1, xl are finally independent and show that this holds. Assume that x1, xl are finally independent. Take any k in L, IL, and now consider xi minus xk's when I is different than k. We wish to show that that collection is linearly independent. So let's take any linear combination of them, which is equal to 0. That should imply that all the coefficients are 0 to conclude that they are linearly independent. Now, assume that Ci I in IL minus k in R is such that Ci xi minus xk I in IL minus singleton k is equal to 0. So this is a combination, a linear combination of L minus 1 vectors in Rn with coefficient Ci. What we need to show is that all Ci's are equal to 0. But what we know is that x1 up to xl are finally independent. Now, this is simultaneously a linear combination of x1, x2 up to xl, including xk. Now, for each I in IL minus k, set Ri equal to Ci, because the coefficients of all such members, that's Ci here, and Rk, this now occurs in each of these terms. So the overall coefficient of xk in this whole sum is minus the sum of Ci's I in IL minus k. So I can write this sum as this. I have just written Ri's are the coefficients of this. And this is equal to 0, thus, and the sum of Ri's, I in I sub L, what's that? Well, here you have the positive version of this sum. So this, the sum of this plus Rk, that's 0. Thus, since x1 up to xl are assumed to be finally independent, these two conditions imply that all Ri's are 0 by definition of affine independence, as x1 up to xl are affinely independent, we conclude that for all I in IL, Ri is 0. So in particular, for all I in IL minus k, Ci, that was Ri, so that's equal to 0. Hence, all xi minus xk's such that I is in IL minus k is a linearly independent set, is linearly independent. So that completes the proof of the only if part of this biconditional. Now the if part is similar. This time you start with coefficients of these and then you produce coefficients for, you start with coefficients for affine independence, then you produce coefficients for linear independence for the set where one of the L vectors is missing. Converse is similar and left as an exercise. Now we'll see that this will be a crucial notion in generalizing points, lines, planes in R3 to similar objects in higher dimensions. This will be the main notion that we will utilize. Now, when you come in here, what dimension would be natural to assign to this? Well, suppose n is 2, then we have n plus 1 is 3. Well, in that case, we take here S3, take 1 point from each. What will the convex hull of this be? Well, that will be this triangle. If they are collinear, it will be a degenerate triangle. So these two edges, well, they will coincide with the hypotenuse, with the larger edge. Well, if this is okay. So, well, if you have here n equal to 2, this will be a two-dimensional object. So if it's n plus 1, this will be an n-dimensional object. Okay? Now we'll give a triangle now can be defined as the convex hull when I consider the triangle as this entire region, as the convex hull of 3 finally independent vectors in R2. A line segment that can be defined, that can be regarded as the convex hull of 2. Will these be finally independent if I take 2 of them? If they're different? Now use this proposition. If they're not coincident, this is x1, this is x2, well, the set you will check for linear independence is this set, x2 minus x1. If x2 and x1 are different than each other, will this be linearly independent? Yes, if it's non-zero, you write C1 times a non-zero vector equal to 0, then C1 must be 0. So that's linearly independent. So these are affine independence. So the collinearity here was for 3, because any 2 points are collinear. You have some line, well, coincident or... Now here, if you have just 1 point, this will be the convex hull of itself. Okay? So let us consider then convex hulls of affinely independent collections in Rn. We will refer to them as simplices. A simplex that will be defined, a k-dimensional simplex that will be defined as the convex hull of k plus 1 affinely independent vectors. What is the maximal number of affinely independent vectors in Rn? Do we have information about that? It can be n plus 1. Because if it's n plus 2, then we will apply this proposition. We will take one of them, subtract that from the set. How many vectors will you get? N plus 1. So they will have to be linearly dependent in Rn. But here, this is in R2, 3 is the maximal number of affinely independent vectors. Now, definition. Let K be a member of N0. Remember, this was the set of all non-negative integers. We add a join 0 to that. And x1, xk, well, and assume that, let me write it like that, and assume that these are finally independent vectors in Rn. Let me write here k plus 1. So k should be less than or equal to n. We refer to the convex hull of x1, xk plus 1 as a k-dimensional simplex in Rn, and to x1 up to xk plus 1 as the vertices of the simplex. But now a question arises. Start with the k-dimensional simplex in Rn. Well, it's the convex hull of k plus 1 of finally independent vectors. Is it possible to also have another finally independent set consisting of k plus 1 vectors such that, for example, x1 prime up to xk plus 1 prime, such that its convex hull is equal to the convex hull of these? If that's not possible, well, then this will mean, well, once the vertices are given, this determines the simplex, but if the simplex is given, then that also uniquely determines its vertices. Well, with triangles, we know, well, if we know the three vertices, we know what the triangle is. And if we know what the triangle is, we can decipher the three vertices back. So, theorem, let x1, xk plus 1, x1 prime, xk plus 1 prime be to the finally independent sets in Rn. Well, I will not write that, but when I say this, I will always mean that these are pairwise different. So I don't have the same vector occurring in both, okay, so, but I will not write that, but that's the case in Rn. Okay, now, well, let me write this equal to C and this equal to C prime. Now, convex hull of C is equal to the convex hull of C prime if and only if C equal to C prime. The if part is, of course, trivial. I mean, You don't need to write that, but this equality implies that C is equal to C prime. I will leave the proof of this as an exercise to you. Hence, when S is a k-dimensional simplex in Rn, its vertex set, and we will denote it by V of S equal to x1 up to xk plus 1 is uniquely determined. Well, if that simplex is a triangle in R2, if you take any point in the convex hull, well, since this is the convex hull of a finite set of x1, x2, x3, you can always write this as a convex combination of the three vertices. How do you refer to the coefficients you use there? Well, you refer to that as the barycentric coordinates of x with respect to this simplex. But for that to make sense, the convex combination of which of these three vertices, which is equal to x, that has to be unique. If it were not unique, well, one convex combination of this is equal to x, but if there existed another convex combination, well, then we would be in trouble. Which one would be the barycentric coordinates? Well, will it be unique in this case? If you have just a triangle, a non-degenerate triangle, and a point in the triangle, well, you can see it will be unique, but it depends upon what? The affine independence. It will depend upon the affine independence of these. If, for example, they're affinely dependent, well, in this case, the convex hull of x1, x3, this will be this. It will be degenerate triangle. Okay? Take x in here. Well, I can write this as a convex combination of x1, x2, attaching zero coefficient to this, but I can write this as well as a convex combination of x1 and x3, attaching zero coefficient to this. So there will be more than one convex combination which are equal to this. So let's formalize this observation as a general result. But we can do that, the formalization and the proof, which will be simple, next hour. Now let S be a k-dimensional simplex in Rn with V of S x1 up to xk plus 1. By definition, x1 up to xk plus 1, they will be affinely independent. Now, for any y in S, which will be the convex hull of V of S by definition. There is a unique lambda, but that will depend upon Y. Now that will be in Rk plus 1 plus with the sum of its components, lambda Iy, I from 1 to k plus 1, that will be equal to 1, such that Y will be equal to the convex combination of the xi's using the components of this lambda y as the coefficients in the combination. In which case, let me write it like that, in which case we refer to lambda y as the barycentric coordinates of y in S. Well, take any y in S. Well, the existence of lambda y, that follows since S is the convex hull of V of S, and this is C of V of S, and V of S is finite. So, well, taking all these members, then any y in S should be a convex combination of them. There is some lambda y in Rk plus 1 plus with the sum of lambda Iy's, I from 1 to k plus 1 being equal to 1, and y is lambda Iy xi I from 1 to k plus 1. The existence part is clear. As for uniqueness, let us assume that y can be written as a convex combination of these k plus 1 vertices in two different ways, using different sets of coefficients. Now assume that alpha 1, alpha k plus 1, respectively beta 1, beta k plus 1 are both in 0, 1 with the sum of alpha i's is 1, and so also is the sum of the beta i's, such that y is both a convex combination of alpha I xi's and a convex combination of beta I xi's, I from 1 to k plus 1. What we know is that V of S, these are finally independent. Now, if I subtract this from that, alpha I minus beta I xi, I from 1 to k plus 1, this is just y minus y, and that's 0. Where the sum of the coefficients here, alpha I minus beta I from 1 to k plus 1, but that's equal to the sum of alpha i's minus the sum of beta i's. But they're both 1, so that's 0. So here we have a linear combination of the x i's, which is equal to 0. Moreover, the coefficients here add up to 0. Since x1, xk plus 1 are finally independent, we conclude that for all I in 1 to k plus 1, alpha I minus beta I, that's 0, that is, alpha I is equal to beta I. So that shows the uniqueness. If these were not finally independent, x1 up to xk plus 1, we have seen then it will have a convex combination representation, but that will not be, in general, unique in the absence of affine independence. Finally, one last proposition. It's a simple one, but for the sake of completeness, let's include that. A simplex S in Rn is both convex and compact. It's the convex hull of a set, so it's convex clearly, the convex hull. Why compact? It's the convex hull of a finite set. What do we know about finite sets? They're compact. But the convex hull of a compact set is compact. That's what we showed at the beginning of last hour. Okay? So, well,